Okay, today's topic is analysis of variance. So we're going to do an introduction to analysis of variance, learning a new statistical technique. So far in this class, we've learned that we can compare whether means from two samples are different, and we do that by using an independent samples t-test. But what if we have more than two samples? Indeed, there are many situations where researchers want to be able to test whether means from more than just two samples are different from one another. As just one example, and one that I will carry through this lecture, what if we think that the type of attachment a person forms with his or her parents in early childhood predicts various aspects of that person's current romantic relationship, including their experience of jealousy, their ability to trust their partner, having a fear of closeness, etc. And we can categorize people according to three different attachment types: having a secure attachment, an avoidant attachment, or an anxious ambivalent attachment. And indeed, in psychology, this is something that psychologists study. So one option we would have is, let's just take some outcome of interest, like the amount of trust these different groups of people report that they have in their current romantic relationships. We could do three separate t-tests looking to see whether there are mean differences between each of the groups. So basically do all possible two-way pairwise comparisons. And typically when we do this with our steps of hypothesis testing, we do our hypothesis testing at a predetermined level of statistical significance. In other words, our alpha level. So each one of our three tests would have an alpha level of 0.05. That is, what we're looking for is a sample result that would happen less than 5% of the time if the null hypothesis is true. The problem with doing three separate t-tests is that we will have an accumulation of experiment-wise error, which is the total probability of a type 1 error across multiple tests. Recall that a type 1 error is when we reject the null hypothesis and conclude that we do have a statistically significant result, even when there's no true difference between the two groups in the population. It's possible to calculate our experiment-wise alpha using this formula. So using this formula, alpha is of course the probability of a type 1 error on any single test, and by convention in psychology as well as other social and behavioral sciences, we use an alpha of 0.05. The K stands for the total number of tests. So this isn't something that you necessarily need to know for an exam, but I'm just making a point about the accumulation of experiment-wise error. Because when we plug in numbers, setting alpha at 0.05, we can determine that three t-tests would have an experiment-wise error rate of 0.143. In other words, there's a 14% chance, a 14.3% chance of making at least one type 1 error across these three tests. So the short of it is, the more tests you do, the greater the likelihood of making at least one type 1 error. So the probability of making a type 1 error increases as the number of tests increase. And again, just to make sure that we know what we're talking about, a type 1 error is when we reject the null, we say we have a statistically significant result, but the two means are not different at the population level. We can never know that, but we set our alpha at 0.05 to kind of limit the probability of making that type 1 error. Okay. So the probability of making these type 1 errors increases. Pardon me. There we go. And so another way to think about this is that an alpha of 0.05 implies that by chance alone there will be one type 1 error in every 20 tests. So for sure, if you do 20 tests, we can think about it would be, close to a 100% chance that we're going to make at least one type 1 error. So it would be nice if we had a way to determine if group means are significantly different from one another using a single test. Wouldn't that be nice? And so indeed, statisticians have developed such a test, which is called an ANOVA, which is short for analysis of variance. This is a hypothesis testing procedure for comparing means of two or more groups. So you can still do an ANOVA when we have two groups. And indeed, the results of an ANOVA and an independent samples t-test will converge and will be exactly the same. That is, if you do a t-test on two means and you do an analysis of variance on two means, you will get a statistically significant result in both cases if indeed those means are different. But once we start having three means, we can no longer do t-tests, or at least we shouldn't do multiple t-tests because of the accumulation of experiment-wise error, so we can do an analysis of variance. In the language of ANOVA, we will do a one-way ANOVA when we have only one independent variable or one predictor. When we have two or more independent variables, we'll do a factorial ANOVA, and that will be a topic for a subsequent lecture. What we do with analysis of variance is we're going to evaluate whether the means of our samples differ more than we would expect them to differ if the null hypothesis is true. Recall that in a null hypothesis, the typical prediction is that there's no effect. And so in the case of looking for differences between three means, the null hypothesis would be that there's no difference between those three means. Those means are the same. They're equal to one another. So the logic is very similar to a t-test, but instead of calculating differences between sample means, we're going to use sample means to calculate variance. But we can just think of the difference between two means as representing variability. Indeed, when we think about how we calculate variance, a variance statistic is based on deviations from the mean. So they're very similar to one another, the t-test and analysis of variance. We're just going to focus on variance because when we want to know how several means differ from one another, we're really asking about the variation among those means. So analysis of variance is based on a somewhat complicated, but I think elegant logic. And so to understand the logic, what we're going to discuss are two different ways of estimating population variance. One method is the method of estimating population variance within each sample. And the second method is to estimate population variance between the means of samples. So what you should have in your mind is that we're using two different methods or two different techniques as a way to estimate the same thing, the population variance. Ultimately, what our analysis of variance does is compares the results of these two different ways of estimating the population variance. So here's the first method, or the first way to estimate population variance. And we call this the within samples method or technique. What we can do is estimate population variance, sigma squared, from the variance within each sample. And this is the exact same procedure as we've been using for the independent samples t-test. Effectively, all we're going to do is get an estimate of population variance from each sample and then pool them together. So we're just going to do a pooled estimate of variance just like we've been doing for our independent samples t-test. This is our within groups estimate of population variance. Unfortunately, analysis of variance has several terms and several symbols. And it's also unfortunate that different symbols in this case mean the same thing. So we're going to use, to stay consistent with notation and terminology that we've been using throughout this course, we're going to use S squared within to designate our estimate of population variance figured using this within samples method. What you will also see in other psychology statistics textbooks or other statistics textbooks for the behavioral sciences or just other statistics textbooks, as well as our own, in fact, is you'll see an MS within or an MS error. So all three of these terms are actually equivalent. So the MS stands for mean square. Okay, so mean square within. So those are all equivalent. It's an estimate of the population variance that is figured using this within samples approach. The second method we have is the between samples approach. And the way that we can estimate population variance is we're going to estimate the population variance based on the variance of the distribution of means. And this is going to be our between groups estimate of variance, which we symbolize as S squared subscript between or as MS between mean square between. So here's the logic. If the null hypothesis is true, all populations are identical and thus they have the same mean, same variance, and same shape. However, even if the null hypothesis is true and the populations have the same mean, sample means that are drawn from these populations will each be a little bit different. And that's the concept of sampling error, is because a sample is a subset of the population. When we take a subset of the population, any statistic that we calculate is likely to be an error to some degree from the true population parameter. That is, a sample mean is likely to differ to some extent from the true population mean, mu. So when we draw, let's say, 3 samples, each one of those samples is likely to differ and be in error somewhat from the true population mean, which, according to the null hypothesis, all population means are equal. So if we go back to our original example and we think about these 3 populations of people that have different attachment styles, securely attached, avoidant, or anxious, and we think about what is the level of trust that they have in their relationships, we've got 3 different populations, 3 different means, but under the null hypothesis, all of those population means are equal. Hence, we're essentially talking about a single population mean. So when we sample from each one of those populations, we should be sampling, even though we're sampling from different populations, we're in essence sampling from the same population under the null hypothesis. So we would expect, merely due to sampling error, that those sample means are just a little bit different from each other as well as from the true population mean. Okay, but we can rely on this because the difference between those sample means allows us to estimate the variance in the population. So let's take a look. Let's look at this left side of the figure, and this is also in the textbook. We've got our 3 different populations of people, and again, let's just kind of imagine that we're working with the example from before, and we want to know what's the average level of trust that securely attached, anxious, and avoidant people have in their relationships. Under the null hypothesis, same exact mean, same exact mu, same variability, okay, so same variance in each of these populations, and same shape. But what happens? We randomly sample 4 people from our securely attached population, we randomly sample 4 people from our avoidantly attached population, and we randomly sample 4 people from our anxiously attached population. Calculate the mean, and then we plot the means. Those means differ to some extent, and the amount that they differ will depend on the amount of variance in the population. Okay? Let's go over to the right-hand side. exact same principle, but what you can see is because there's more variance in these three populations, but it's essentially the same population variance, we see more spread among these three sample means. Okay? So therefore, the amount of variability that we see or could calculate among our sample means allows us to provide an estimate of how much variability there is in the population. If we calculate that there's more variability among these sample means and there's less variability among these sample means, that would suggest more variability in this population, less variability in this population. So there we have it. The variability among sample means reflects the amount of variability in the populations. All right. So following this logic, again, if the null hypothesis is true, which means identical population means, identical variance, identical shape, then the population variance estimated from the variance between sample means should be the same as the estimate of variance figured within each sample. Okay? So in other words, figuring out what the population variance is, that is, what is basically the spread of this distribution, figuring it out using this between means approach, that should converge on the same estimate that we would get using the technique that we've already learned, which is the pooling together of the estimates of population variance from our sample variance. Those two things should converge. So the between should converge on the within. However, if the null hypothesis is not true and there are differences between the population means, then the estimate of population variance that is estimated from the variance between the sample means, down here, should be more than the estimate of the population variance figured within each sample. This is because the between group variance now reflects differences between the population resulting from some true effect or treatment. Okay, so in this case, maybe I should have, in this example, had this distribution been my secure folks, because there's likely some true effect in the population that securely attached people report higher levels of trust. So if we've got a number line here, higher numbers, smaller numbers, this is the amount of trust, we would expect on average people that are securely attached to report more trust in their relationships than people that are anxious or avoidant. Okay? So the only thing that's different is the amount of variability between the sample means. Under the null hypothesis, same amount of variability within each sample. That hasn't changed here. But what's different? The amount of variability that we have between our sample means. Okay, so continuing this logic, if the null hypothesis is true, the within group's estimate of population variance reflects variation due to random chance factors. And the between group's estimate of population variance also reflects variation due to random or chance factors. That is, under the null hypothesis, how come everybody's not the same here? Well, statisticians chalk that up to randomness or chance. We know that there's individual differences, of course, but a statistician chalks that up to randomness. And why are there differences between these means? Well, they're all supposed to be the same, right? Well, they're different just due to randomness. That's under the null hypothesis. However, if the null hypothesis is not true, the within group's estimate of population variance still reflects variation due to random chance factors. However, the between group's estimate of population variance still reflects this variation due to random chance factors plus variation that is due to some true effect or treatment. Okay, here's all the animations again. But under the null hypothesis, or if the null hypothesis is not true, the between groups estimate of variance will reflect some true effect or some true difference. All right. So that's the only thing that's different. And so this is a nice table that is in the textbook that reflects that logic as well. So if the null hypothesis is true, the within groups and the between groups estimate should basically be the same because they merely reflect variation due to chance factors. However, if the research hypothesis is true, the between groups estimate of population variance should be larger than the within groups estimate of variance because in addition to these random chance factors, it also reflects some true effect in the population. So what we do with ANOVA is we create a ratio. We're going to look at a ratio of the estimate of population variance figured between to the estimate of population variance figured within. If the null hypothesis is true, both of these methods should converge on the same number, the same estimate, because they really just reflect chance factors or chance variation. And therefore, the ratio of the s squared between over s squared within should equal 1. However, if the null hypothesis is not true, the estimate of population variance using the between means approach or the between groups approach should include a treatment effect or some true effect in the population, and therefore this ratio should be greater than 1. So the statistic that we're going to calculate is the F ratio. And this is this crucial ratio of the between groups to the within groups population variance. And it's named after Sir Ronald Fisher, the person that came up with this statistic. So just how big does the F ratio need to be? As you might expect, there is a statistical distribution to tell us. So this is the F distribution, that much like the T distributions that we've been working with, or like the normal curve, this is a mathematical distribution. It's equivalent to saying what would happen if we randomly selected a large number of samples of a particular size, and then we figured the F ratio each time, and then we put that F ratio in a pile. And then we repeated the process many, many, many times. What this F distribution will tell us is under the null hypothesis, what is the size of the F ratio that we can expect just due to randomness or due to chance. What you'll notice with this particular F distribution is that most of the time under the null hypothesis, we're going to expect an F ratio that is right around 1. However, sometimes we'll get an F ratio of 2 or 3 or 4. And that could happen not due to any real effect, but due to some random or chance factor. So what we're going to ask is, how big does our F ratio need to get before we say, hey, that's not randomness or chance, that's due to some real treatment effect or some real difference in the population. And so we have an F distribution lookup table that we'll use very similar to our lookup table for our T distributions. Okay, so just some properties of this F distribution. The mode is always 1, that is the most frequently occurring F under the null hypothesis is 1, because that ratio of S squared between to S squared within should be the same, it should be 1. We always have positive numbers. Why? Because a variance is a squared statistic. And with a squared statistic, it is impossible to get a negative number. So we're always going to be looking at a ratio of a positive number over a positive number. It's a ratio of a positive to a positive. So our F, any F that you should ever calculate should always be positive. And it will always be positively skewed with the mode around at 1 and then becoming progressively less likely or less probable to have very high Fs. Okay, So let's do an example that will hopefully make this a little bit more concrete. So we'll go back to the example that I led with, and we're going to ask, does the type of attachment a person forms with his or her parents in early childhood predict the amount of trust that they feel toward their romantic partners as an adult? And this is actually a question that relationship psychologists study. What I'm going to do is take you through an example of how to calculate the F ratio. And then what I'm going to do is bring back our 5 steps of hypothesis testing, because we're going to test hypotheses regarding doing an analysis of variance and regarding whether multiple means are different from one another following our same 5-step approach. But just to get the logic down and the calculations down, I'm going to skip that and then come back to it. All right, so some researchers asked people to respond to a love quiz in a local newspaper, and respondents classified themselves as either secure. So securely attached people would answer or indicate agreement to items like, I find it easy to get close to others, I am comfortable depending on them and having them depend on me. So people with a secure attachment would agree with statements like that. People with an avoidant attachment would agree with statements like, I am somewhat uncomfortable being close to others, I find it difficult to allow myself to depend on them, I get nervous when anyone gets too close. And then people with an anxious ambivalent style would agree with statements like, others are reluctant to get as close as I would like, I worry that my partner doesn't love me, I want to merge completely with another person, and this scares some people away. So we've got those 3 styles, and we're going to ask the question whether these 3 different groups of people that have these 3 distinct styles experience and report different amounts of trust in their romantic partners as adults. And so people in this study just responded to the item, I feel complete trust in my partner, on a 5-point scale where 1 is strongly disagree and 5 is strongly agree. So higher numbers indicating more trust. And here's fictitious data which is loosely based on that original study. But we've got 5 people in each of the groups. We've got the mean trust reported, and then we've got the estimate of population variance figured from each one of these samples. Okay, so where did this calculation come from? I just calculated with you can imagine having each of these 5 people. They reported a trust score ranging from 1 to 5, calculated the variance, and then instead of dividing by 5, we divide by degrees of freedom, and that gives us an estimate of the population variance. Okay, and so that was done for each of these 3 groups. Okay, so if these are the data, the question is, does the amount of trust people report differ depending on their attachment style? Okay, kind of looks like it, doesn't it? That with this mean of 4.2, but we're going to say, hey, are these means different from one another? That's what our analysis of variance will allow us to do. Ultimately, our goal is to calculate this F ratio. This is the statistic that we need, and we're going to look at the F ratio that we calculate, and we're going to compare that to a critical value of F in a lookup table. But let's just go over the calculations first. So we're going to use our 2 methods for estimating population variance. And so our first method is to estimate the population variance from the variation of scores within each group. So this is essentially just our pooled variance procedure. All we're going to do is take the simple average of the variance estimates from each sample, and we're going to divide by the number of samples or groups that we have. So to do this, all we're going to do is add up our 3 estimates of population variance and then divide by 3 because we have 3 groups. Okay, so there we are. We got each estimate of population variance. We're going to add those together to divide by 3. So we get that our estimate of population variance figured using this within method is 0.67. You'll notice that this is nothing more than taking a simple average of the three estimates. Okay. Now, you might remember from our t-test that we had to do a somewhat complicated procedure where we took a weighted average. Our pooled estimate of variance often had to be weighted by the relative degrees of freedom, okay, another or sample size from each group. We can use this simple averaging procedure because and only because we have the same sample size in each group. So we're weighting each one of these estimates equally because sample size is the same. And for the calculations that you will do in class, it will always be the case that sample size is the same, okay? In the real world, when we're using a statistical software or a statistical package, we don't have that limitation that sample size needs to be the same. But that's just kind of a simplifying assumption just to illustrate conceptually how the statistic works. In the real world, you don't actually have to have the same number of people in each group. All right, so that's our first method. Second method is to estimate the population variance from the differences between the group means. Okay, and so this is kind of a two-step procedure in order to do this. The first thing that we're going to do is we're going to estimate the variance of the distribution of means. Okay, so this is based on the logic that each of the means from these three groups, it kind of starts to form its own distribution of means. Okay, and so what we're going to do is take our variance formula, and we are going to use that to figure out the variance among our sample means. Instead of an x, each one of our means is going to be kind of that like individual observation. So previously we had an x here, and now our mean is going to be the grand mean, the mean of means. So we're looking at the deviation of each of the sample means from the grand mean. We're going to square that deviation and then divide by degrees of freedom. So you notice that this is the exact same way that we've calculated an estimated variance. What we're then going to do is we're going to get an estimate of the population variance based on the variance of the distribution of means. And we're going to do that by taking the estimated variance of the distribution of means and multiplying by the sample size. And where this comes from is essentially our rule 2a under the central limit theorem. Recall that if we knew what the population variance is, we can calculate the variance of the distribution of means by taking the population variance and dividing by n. We've done that calculation many times in this class, where we've taken the population variance or an estimate of the population variance divided by n, and that gives us the variance of the distribution of means. So the kind of subtle logic here is we're just working backwards. If we don't know or if we're trying to get an estimate of the population variance, but we have the variance of the distribution of means, we can then just rearrange the formula, and instead of dividing by n, multiplying by n, and that way we get the population variance. All right. So first step, to figure the between groups estimate of population variance, we're going to estimate the variance of the distribution of means. So we're going to treat our three sample means as a mini sampling distribution. And we're going to say, how much variability is there among these three means? So the first thing that we need to do is we need to calculate the grand mean. So I've done that here, and I've just taken the average of 4.2, 3, and 2.6. And so you can do that on your own, but you'll see when you do that, the mean of these means, otherwise known as the grand mean, is 3.27. What then I'm going to do is use our good old variance formula, take each deviation from the grand mean, square it, sum it up, and then divide by degrees of freedom. Notice that we have degrees of freedom between, because we're using the between groups method, and we've got three different means that went into this calculation. So we're going to take 3 minus 1 is 2 degrees of freedom. Okay, so here's what that looks like. So again, we're figuring out the variance of the distribution of means, treating each one of these means as an observation. We don't have all the observations in this distribution of means, but we're using them as kind of a sample, okay? And that's the reason, by the way, that we're dividing by degrees of freedom. These 3 means are only 3 of the possible means in our distribution of means. Therefore, we've got a sample and not the whole thing. So whenever we have a sample and we're trying to get an estimate of something based on a sample, we divide by degrees of freedom. All right, so that's our first step. So what we get is our estimate of the variance of the distribution of means is 0.69. Now what we have to do is a second step, which is to figure out the estimated population variance based on the variance of the distribution of means. And so we do that by rearranging our previous formula that we've been using under Rule 2a of the central limit theorem. So instead of dividing the estimate of the population variance divided by n to get the variance of the distribution of means, we're going to just now multiply the variance of the distribution of means by the sample size to work backwards and get the population variance. So we do that. We're going to multiply by 5 because that is our n, our sample size, and we get a estimated population variance of 3.45. So now that we have both our s squared between and our s squared within, we can figure out our F ratio. Okay, we do that by taking that estimate that we just got of 3.45, our s squared between, dividing that by 0.67, which is what we previously calculated as our s squared within. That gives us an F ratio of 5.15. Again, just how big does that F ratio need to be? We need to compare the F ratio that we calculated to a critical value. The critical value for the F ratio is determined using 2 sets, we can say 2 different degrees of freedom. The first is degrees of freedom between groups, which is just the number of groups minus 1. So we had 3 groups, minus 1 is 2. And then degrees of freedom within is calculated by determining the degrees of freedom within each group and then adding all of those together. Okay, so we had 5 participants in each group, so 4 degrees of freedom in each group. 4 plus 4 plus 4 is 12. So our critical value with an alpha of 0.05 for a critical value of F with 2 degrees of freedom between and 12 degrees of freedom within is 3.89. And we determine that using a lookup table. So the leftmost column is the denominator degrees of freedom. The denominator is the bottom of the formula, the bottom of the F ratio. So we had the bottom of our F ratio is our S squared within. So we need degrees of freedom within is 12. And then our columns are the numerator degrees of freedom. The numerator is the top of the formula, the top of the ratio. And so we had, that's our S squared between, we had 2 degrees of freedom between. So looking at, and then for each, we've got our 3 different alpha levels here, 0.01, 0.05, and 0.1. So 12 degrees of freedom, alpha 0.05, 2 degrees of freedom between, we get a critical ratio of 3.89. So that's how to use that table. So before reaching our conclusion, let's just go back and work in all 5 steps of hypothesis testing because we're going to use the same 5 steps that we've been using throughout this course. So we're going to restate the question as a research hypothesis and a null hypothesis about populations. Population 1, I'm just arbitrarily going to say is secure people. Population 2, avoidant. Population 3, anxious, ambivalent. It doesn't really matter. It's pretty arbitrary who we're assigning to population 1, 2, and 3. Under the null hypothesis, we're just going to say that mu1 equals mu2 equals mu3. And our null hypothesis for analysis of variance will always be this. that mu1 is equal to mu2 is equal to mu3. Pretty simple with analysis of variance. This is the only null hypothesis that we'll have for this overall one-way analysis of variance that we're going to do. And then our research hypothesis is that the population's means are not the same. Not the sample means, but the population means are not the same. And this is also the only alternative or research hypothesis that we will have with this one-way ANOVA. So in this respect, analysis of variance is a little bit more simplistic, is that there's only two possibilities for, I beg your pardon, there's only one possibility for your research hypothesis, there's only one possibility for your null hypothesis, and you're looking at them. Oops, animation's a little bit messed up here. So we're going to determine the characteristics of the comparison distribution. We've already determined with our example that this is an F distribution, and we've determined that we've got 2 and 12 degrees of freedom. That's how we calculated it. There we go. We're going to determine the critical value on the comparison distribution. We do that by using our degrees of freedom and using our lookup F table. So that number is going to be 3.89. And again, it's always positive. We always have a positive critical value with analysis of variance. We're going to determine our sample score on the comparison distribution. In order to do this, we've got 3 calculations. We first need to calculate the within groups estimate of variance. We second need to calculate the between groups estimate of variance. And then third, we need to put those together in a ratio. And in doing that, we got a ratio of 5.15. Last step, we're going to decide whether to reject the null hypothesis. And in this case, our F ratio of 5.15 is more extreme than our critical value of 3.89. So therefore, we do reject the null hypothesis. We can conclude that the differences observed between the groups are greater than the differences that are expected by chance if all samples, sorry, typo there, if all samples were drawn from populations with identical means. Okay? So what we've done is we have shown that there is simply too much variability between the means to accept the null hypothesis that all of those means are drawn from populations that have an identical mean. There's too much variability there. So we are going to reject the null hypothesis. Recall that the null hypothesis was that mu1 is equal to mu2 is equal to mu3. So that's what we're rejecting. And we're saying essentially we're saying like those means are not all equal. And the conclusion that we can make at this point is that people having the 3 different attachment styles differ in the amount of trust that they feel toward their romantic partners. All right. But how do they differ? It certainly looks that securely attached folks report more trust than the other groups. But is that the case? Or is it the case this 3 looks different than this 2.6, but is it the case that avoidant is greater than anxious ambivalent? Our analysis of variance test does not allow us to answer these specific questions. All the analysis of variance allows us to do is say that at a population level, our sample means are drawn from populations that don't have an equivalent mean. But as of right now, we don't have the ability to be more specific than that. What we have to do are follow-up tests. So after a significant analysis of variance, we have to do follow-up tests to see which means are different from the other means. And that will be the topic of a subsequent lecture.